pick up from here. So either when the speaker presents, when the speaker uses his microphone, then I'll switch back to the just audio level.
Okay. So maybe it would be good to do the introduction of it. Oh, don't be afraid. The first row is still okay. So it didn't change in 3 years. People are still afraid about the first row. The problem, if we remove the first row, it doesn't change anything.
What you do is wait for everyone to sit down, and then we take the seats away. That's one way. Otherwise, you do the school way. Wait for everybody to sit down. So you, all of you at the back.
Yeah.
Oh, there's a little guy here. You can see it. Come with us. So the camera will be here, so you need to speak around here.
I think you're ready for the opening.
So, no, it's good. It's the first time we are all the four together in person. For 2 years.
And a half.
So welcome everyone. Just that's the thing we just figure out that as an organizer of the Java user group, you have the chance to have the four of us live for 2 years and a half. You don't know what chance you have, but actually it's so thank you. So now I let Michael start in.
Sure. Yeah,
it's a good idea. We move this.
Thanks everyone for coming. So we're super happy. It's been 2 years and a half that we didn't do any face-to-face meetup. So we tried very hard to do online meetups, but it was not so fun. No pizza, no mingling, just a talk. So we are very happy to have you. And yeah, so for the first time, so we have a visitor to Singapore. We have John, who is CTO at Hazelcast. And yeah, so we will do a talk about Kafka and Hazelcast. Jerome, you want to do? No?
I'm taking a picture.
Okay. You want to say one or
no, we're just really happy that we can kickstart a normal life for meetups. And as you see, we learned from the COVID. So now we try to have our meetup hybrid. So it's also live cast from YouTube for people who do not have the chance to eat pizza. So, sorry, we didn't have pizza.
Thank you, John. Patrick, so Patrick is from Palo IT. That's our sponsor for tonight, for the place and for the food.
Hi guys, welcome to Palo Office. This is, as the guys were saying, it's actually our first meetup where not only in the Java user group, but across all the communities from meetup that we received, that is visiting both our office in Scalable and our new office. Some of you might have realized while looking for it that our office was at Botkey, so I don't know if Grab sent you at the wrong place and you walk all the way here. We moved here a year plus ago. Anybody doesn't know Palo IT? I guess some of you don't know what we do, who we are. We are a global innovation company. with a footprint in a number of countries around the world. We are not very big, but we are big enough to matter all across the world. And we have a strong focus on technology for good. So a lot of the work we do is about how to make our environment better, the work with our people better, and so on. And this is an example of it. One of the values of the company is sharing, and another spirit of sharing. That's why we host regularly meetups events like the one organized by Marco. With this, I give back to you. Yeah, and we can go into the specifics.
Thank you very much. Okay, so now we'll have John talk about Kafka and Hazelcast. Thank you very much.
Thank you.
Well, I'm very excited to be here today. Everyone able to hear me okay in the back?
Yes.
I came to Hazelcast 4 years ago. Yeah, 4 years ago. Sometimes it seems longer. From Cloudera. And when I saw what was possible with this technology, which I'll explain more about, you know, I was just blown away that you could do a lot of the things we were trying to do at Cloudera, but more real time and in a much simpler architecture. And so that's, yeah, it's pretty exciting, and it enables a lot of use cases that you actually couldn't possibly do on Cloudera, which I'll talk more about in my talk. But first I wanted to, I'll bring this up at the end as well. We're going to do a drawing. Anybody who's willing to put your information in, then someone in our marketing department tomorrow will do a $100 gift voucher. I don't know what the one is. It varies from country to country, but it'll be something appropriate for Singapore. And you just have to identify yourself so that we can then spam you. That's basically how that works. So before I get into some of these examples, I just want to know sort of how many people have used Kafka before? Okay, so most of you have at least heard of it, but at least half of you have used it. How many people have heard of Hazelcast before today? Only a few. Of the people who've heard of Hazelcast, how many people knew that we had a streaming analytics capability, real-time data processing capability? Oh, so 1/3. That's about what we see normally. And were you aware that we had SQL capabilities? So yeah, I just kind of asked those things because I think it's interesting to see, you know, what the awareness level is, and hopefully more of these talks will get people to realize Hazelcast has come a long way since we were created and introduced into the world about 10 years ago. Well, why am I here to talk about real time? You know, I want to talk about a few examples of what do we mean by real time. First of all, our CEO would say real time is any deterministic business SLA, not a technical SLA, that drives, you know, an architecture and a requirement around data processing, you know, is what we define as real time. So it could be real time means consistently processing a certain amount of time of data within 1 hour, but being able to do so, you know, consistently, predictably, even under heavy loads, busy days of the year, even if it's securities trading during like a crazy high volatility trading day, for example. Or it could be, you know, some other examples are we have a pizza delivery company in the US who uses Hazelcast in a pizza tracking app, and their busiest day of the year is Super Bowl Sunday. The US Super Bowl is the championship for American football. It's the one we play with our hands and not our feet. I'm actually more of a normal football fan, or what US calls soccer. But some other like latency SLAs. The first one I always bring up is Google has something called their rail model. They've done extensive research on user experience, and they've determined that anything more than 100 milliseconds and if an app is not responding back to you clicking on a button or interacting with the UX, whether it's mobile or on your browser or wherever, then it's perceived of as broken. So 100 milliseconds, if your app isn't responding, then it feels broken. A lot of people don't realize just a regular website or a mobile app needs to think about low latency and real time. And by frame of reference, a blink of an eye is 100 to 400 milliseconds. So basically, as fast or faster than a blink of an eye is how quickly an app needs to respond. So that means that every company that has apps that are used by people should care about real time. Some other latency windows, 40 to 50 milliseconds is your typical window to authorize a credit card and also to do any kind of fraud checks to determine whether or not that's a suspicious transaction and it should be blocked. If you take any longer than that, you could identify fraud and send someone a text message or push out a notification through the app, but you already needed to have authorized the transaction, which means if somebody is trying to take a stolen card and buy a expensive TV in the US, we don't even have a PIN required even for large dollar transactions. And so that means that somebody could buy a $5,000 television with a stolen card, and you might get an alert and say, nope, that's not me, block the card. Legally, they have to not charge you as a customer if it's within a certain period of time for transactions if you responded to these alerts, which means that your bank or credit card provider has bought a TV, because Best Buy has an approval code, or whatever retailer. So there's all kinds of windows of opportunity. If I want to make a personalized real-time offer, we have banks who are analyzing what you're doing, and they're pushing it out while you're banking and making offers around, say, credit products or other products. Maybe they're cross-marketing and promoting with retailers to do buy now, pay later types of things. The window of time, again, it might be milliseconds. But there's other things like how quickly do you want to calculate risk? That might be minutes, hours of time that you do risk calculations in banking. Typically, that's not a real-time calculation. On the other hand, there might be some things like, if you're calculating things related to FX pricing or to haircuts on leveraged trading, there might be real-time risk-related calculations. And then, medical devices, obviously medical systems need to respond in real time. So, I just provide a few of these different examples, responding to equipment failure to prevent that failing, just to kind of stress that this technology is pretty relevant to a wide range of use cases. And what's unique about Hazelcast is that we have capabilities for processing data in motion, such as that data that's moved around and stored with Kafka, as well as data at rest in one runtime. So our history was we were an in-memory data store that was distributed. Sorry, I'll try not to move around too much. Distributed and partitioned, and so your data would land on any of a number of different nodes of a cluster, and then we would also replicate the data to other data centers so that you could have very, very high levels of uptime, and that zero downtime architecture where you have real-time active clusters that are synchronized, and the data within the clusters is partitioned, but there's backup copies on the cluster so that you don't ever lose data. That's kind of the heritage. And over time, we've made that more and more resilient and consistent, and also added a lot of capabilities to be able to query and do computations on the data that we were holding in Hazelcast. And as we did that, we started to realize there was huge value in bringing computation together with data and combining it with distributed, partitioned processing. And so that led us to adding this ingest and processing capability into the platform and this slide will advance. Maybe an arrow? I'll use the arrow. So that led us to introducing our stream and batch processing engine into the platform. So the bottom component of that architecture, a lot of people would compare to something like Redis. The top layer of that is comparable to Apache Spark or Apache Flink, except that we can provide the same kind of data pipeline processing as those technologies, but we can do so in a way that is very high throughput and low latency, and we'll talk about why that is. But we've done a lot of benchmarks, and I'll just say that we crush Flink and Spark, and in fact, vendors who promote those technologies, they don't even attempt to go after use cases of less than 500 millisecond latency typically, and certainly not high throughput combined with low latency. So that technology really has some significant advantages because of the way we're combining things together. We're combining the compute and data while also taking advantage of the ability to make that very parallelized, the processing. And at the same time, we have a data-aware capability, meaning that wherever the data lands in the cluster, we know what data is in what partition. And therefore, we can make sure that the compute related to, for example, my data that's sitting in my partition for my account or my securities trades might be in one place, and somewhere else is Paul's data in a different node, and so we're not moving data. We don't move the data. Instead, we process it and analyze the data where it lives. There's some other advantages. We have a collaborative work sharing mechanism that means that we don't have to have a master worker architecture, and that simplifies the operational aspects of the cluster. Combining that with the fact that we have a single jar file architecture means that if you're a Java developer, you can get started with Hazelcast with one line in your Maven file, and when you're deploying it, that it's just another Java application that you're deploying and managing. We optimize for in-memory, which further drives down latency. We do SQL as well, so that we can actually combine data that's coming in from Kafka with data that's sitting in Hazelcast, so that you could enrich the streams of data with contextual data. So you might have payments that are coming in, and you want to add information about the customer's current balances and other core banking data, but maybe you even want to add in data about other things that about that customer, but also maybe even data that's not related to that customer, but related to broader trends. Any data you could store in Hazelcast and integrate with real-time data to make richer decisions, and so that's very powerful when you get into some of the use cases. So, the main goal of this talk is to talk about the enemies of performance, and then really introduce technologies that could help you address those. So really the first enemy of performance is the network. Every time you're moving data over the wire, that adds latency, and you can't get rid of the latency, right? Because networks are governed by the speed of light. And so unfortunately that's something that we haven't figured out how to get work around. There's also storage bottlenecks. There is processor bottlenecks and switching. The CPUs, if they are having to kind of switch between different sets of instructions and things, the way that the code works, that can often add to bottlenecks in performance due to context switching. And then overly complicated architectures definitely add to the latency. So a good example of this is a Lambda architecture. A lot of people who are big fans of Kafka will, have data coming in from Kafka, and then they need to analyze it, so they start to put the data into a database. At the same time, you have the data coming in on Kafka in real time, and the database has to store the data before it can query the data. And so what will happen is you'll have a mismatch between what does the data look like that's coming in right now and what is your query results. And that might not seem like a huge problem, but when you get into these low latency use cases, it can be a very big problem in terms of that impedance mismatch. But it also means a more complicated architecture. And then if I'm trying to use this architecture to support an application that people interact with, that application, if it's real time, may have a tier 1 or tier 0 very high uptime requirement, and Lambda architectures are terrible in terms of delivering 5 nines. Another architecture that is not a good real-time architecture, even though some of the vendors who are behind this kind of an architecture, including my former employer, would claim that they can deliver a real-time experience, but you could take a look. You have like data landing, then there's some processing, then it's stored, processed, stored, processed. So you have this kind of ping-ponging of data. Every single step, there's at least a movement over the network. There's maybe also movement of data onto disk or solid-state disk and back off. And very complex architecture to maintain. This is not going to be a 5 nines architecture. I mean, it's just not. It's hard enough to even get this working reliably and resiliently in one data center with a predictable SLA of response times, let alone what happens if you lose a data center. That other data center is going to be not in sync with all of these different components. So another example of Hazelcast compared with the Apache Spark architecture. I'm not going to go into the details, but you could just take a look and you can see that there's a lot of moving parts on the one side, and depending on what fails, you don't really know the implications of whether you're available or not, or continuing to process or not. In Hazelcast, every node has some data. It also is doing some compute, and it doesn't matter what node, their data is always backed up, and the compute will be transferred and restarted on another node. So basically, if you have n nodes and you lose one, it's 1 over n is your loss in capacity of both compute and data. So this is really kind of the, rubber meets the road, picture for me. Every single one of these nodes is processing, data. They're all peers. And because they're all also processing data and also storing the data, and they're aware of where the data lives, it's very powerful in terms of being able to do real time. Because it's also in memory, at least the data that's actively being processed, then that also further improves your performance. But now we can also bring that together with things like machine learning and say, okay, well, what if the machine learning is fed this data? One of the things about machine learning is that machine learning needs very rich data, right? You can't just take raw payments and feed it to machine learning. All you're going to get is, a very simplified pattern that doesn't really tell you a lot. Same thing would be true if you were feeding it sensor data. You need to enrich that. I mean, if you send someone a machine learning algorithm, a bunch of sensor data, like a temperature sensor, well, is that an air temperature? Is it a fluid temperature? If it's fluid, it could be a coolant or a lubricant. Is it attached to your car or a giant, industrial piece of equipment, or maybe even a power plant? That context really is what is fed to the machine learning in order to allow it to do the great things that you can do with ML. But if you don't have rich data, then your ML is not really going to add a lot of value, and you might as well just be looking at very simple computations on the data and basic math. So anytime you're talking about machine learning, but you also want real time, you need rich data pipelines, and I don't know how you can do it without a heavily custom architecture, optimized, custom coded for your use case, other than using Hazelcast. Single jar file, so when you're deploying this into production, it's just a Java application. If we were to look at payments, trades, or it could be a shopping cart, you're putting stuff into the shopping cart. I would like to make real-time offers. My data is going to be on a different node in a different partition than someone else's, and that's really kind of the power of the real-time. So in terms of performance, I talked a lot about performance. You always want to hear some numbers. So we've done benchmarking where we were able on 45 nodes to see linearly scalable increases in throughput. The power of that is that we started at a very small number of nodes and we were already doing millions of events per second. Kafka is very good at moving millions of events per second, but Kafka streams is not going to process millions of events per second, let alone a billion of events per second. So Hazelcast is able to scale linearly to over 1 billion events per second. A billion was reached at about 45 nodes. We were delivering under 30 millisecond latency at 99 percentile on this query. This was a real world benchmark that we found, an industry benchmark. It wasn't our benchmark. So there's a link to the blog where we publish all of the details about that, so anybody could, take and recreate that, because we don't ever believe in talking about benchmarks if we don't provide all the transparent information around them. We actually published this and we thought we're really just trying to prove that we're efficient, but we didn't think anybody needed a billion events per second, and there was a company in the media space in Silicon Valley that reached out within a week after we published this and said, could you guys do 10 billion? So there are companies out there that do need these kind of crazy throughputs. But I want to talk a little bit more about the architecture behind it. One of the things that you can do with any kind of technology like looking at Kafka and pulling the data off is that you could then take that input and partition it and process that in a way where you're avoiding serializing the inputs. And so you can say, John's data needs to be partitioned out, or data about Apple trades versus Amazon trades. Maybe we'll partition those. So we can get into partitioning with some clever programming. But if we want to go one step further, and this is looping, there's still a lot of looping that has to happen. How do we get around that bottleneck of processing things in order? We actually can go further and take partitioning and combine it with pipelining and work with data in a pipeline, because we often need to do a series of calculations on the data, right? We need to first, filter the data, then we want to do some like sums or averages or aggregation of the data. Maybe we need to join streams together. Each of these stages of the pipeline, it's really a fairly simple API that we have. We were inspired by Java util streams with how we built our pipeline API. And reading from Kafka is a fairly simple, small bit of Java code. And then we can, break this into stages where each stage potentially is doing a separate set of transactions. So filtering, and then we need to enrich. So we've got data coming from Kafka, and we want to look at some data in IMAP, which is Hazelcast's basically like a distributed hash map concept. And we could enrich that data, but because we've, say, partitioned the data coming from Kafka in a way that is intelligent, but we also have the data partitioned with data affinity rules in the map, then we can make sure that when we filter the data and say John's data, is going in and, being fed, so we can look at the keys of the data and start to spread the work out, and then also look at the the information in the maps, and again, it's partitioned. And then we can start to do some calculations, and then of course we can write that back out to Kafka in this case. So, what does this look like? Because we have broken it into steps, then we can now put queues between the different steps. But these queues are not Kafka, they're not on Kafka. This is all within Hazelcast, and this is all optimized in memory. And so from between each step, you have tasklets. And these tasklets can be distributed and executed in parallel on different threads or even on different nodes. And so as we move with the data through from one queue to the next, one tasklet to the next, we also may have different types of data. And all of this is being represented in a directed acyclic graph. You don't need to know what that is, but it's basically a one-way data pipeline where you have a mutable data moving through the pipeline. The data is changing, but it's not, from one stage to the next, it's immutable. And so what you're able to do when you compare this was just a colleague of mine ran some simple benchmarking and just was able to look at how many time units, when you don't do any partitioning and pipelining, you could process three things, right? You process all the data for one thing, all the data for the next thing, all the data for the third thing. Then if you start to do some partitioning, then we can use more cores on our single node of a cluster. And so because we can use more cores, then if it's 2 cores available, we could potentially parallel process. Depending on what keys we're using with the partitioning, maybe we could use some more cores. When we do pipelining, we can use more cores, and we can now get 15 time units versus 3 or 6. If you combine these two together, eventually, you can start to get up to 15 time units and, much more parallelization. It's not a super easy to use diagram or read diagram when you first look at it, but I think it sort of conveys the point that we want to parallelize as much as possible. And if we can break the processing down into steps, each of those steps, if it can be parallelized and if it's also data aware, then we can start to get some tremendous improvements in both throughput and also latency. So some of the basic building blocks of this streaming engine, we used to call this engine Jet, and it used to be kind of an add-on component to our data grid, and we last year unified them together so that there's just one runtime, one product. One of the reasons we did this was to make it easier for people to adopt the technology, but another reason was it actually allows us to innovate faster because we're not maintaining 2 different code bases, and we can deliver more value to the market. We're then able to do stateless transforms. So some things can be extremely parallelized because they're stateless. So filtering, mapping, transforming, merging streams together. All of these things, if I'm working with John's data and merging my shopping cart with my shopping cart history, with my products and interests, with information about my web clicks and what I'm clicking on at that one moment in time, all of those pieces of data can easily be merged together, and that can be very efficient, parallelized, and each step of that type of processing can be running on lots of different cores and lots of different servers because, Paul's data or Michael's data would be potentially running somewhere else. So now we're going to get to a demo, but I wanted to just talk a little bit about the demo. It's a continuous query with drill down demo. We have this kind of Lambda architecture, but now it's running on Hazelcast. It's all running in one runtime. And so the trades that are coming in are actually at the same time being continuously aggregated. And so you're able to see everything that's coming off of Kafka and also do aggregation enrichment of the trades with data that's held in Hazelcast so that you have this, consistent picture of the data. Am I not sure? Oh, maybe I need to end the presentation. So this is our trade monitor demo, which there'll be a link to in the presentation, which we'll share with the organizer for you guys to share. You can also find it pretty easily on Hazelcast's developer pages and documentation, or on our GitHub. You can see that trades are coming in, and we're actually looking at all these securities that are being traded, and we're aggregating. So we're basically looking at all the pricing and rolling it up and calculating the total volume, and also analyzing and determining are the prices going up or down. One of the things we're also doing is we're filtering out any trades that are securities that may be currently being delisted or that are for some other reason considered sort of securities that we don't want to present to our algorithms or traders or whatever. So there's an enrichment step that's happening as well. And then, what traders will typically want to do is, as they start to see that a stock is moving up or down, they may start to see some big trend, and they want to drill in and see, like, what's really going on. Is it, a few big investors that are making some big trades that are driving that volume, or is it a lot of little trades from small investors? Or maybe it's a lot of little trades from algorithms that are driving it, and those algorithms are driving a bunch of volume that they're going to then do a big trade on. That's the one that they really care about, and the other trades are all just trying to trick other algorithms. And most high frequency at least, algorithms are not trying to trick people anymore. They're just trying to trick other algorithms. So, one of the things you might also want to do, of course, is actually query. And so we do support now SQL, and you can't really see this data very well here, but it's actually doing a join with data that's in Kafka and data that's in Hazelcast. So we're basically, looking at this and going, well, that's really interesting, but I want to go and run a new query, and I want to pull some of that data from Kafka, and we're able to just go ahead and do that. And I can go into our management center. Let's just make sure this is, and then in our little SQL browser, we could start to execute this query, and you can see a better view of what the SQL looks like. So KF trades is a Kafka topic, and you can see it here in CoffDrop. And so the trades are actually coming in, and this is a JSON, and we're taking the JSON data, pulling it into Hazelcast, and able to easily combine that data with data that's in Hazelcast that could have been loaded in advance from various other databases, or in some cases it could be directly written into Hazelcast. We have a lot of people who have their online applications writing to Hazelcast, and then we're also replicating out to other applications. So when you write into a Hazelcast map, we can asynchronously write that data out to another database, whether it's a a typical like a SQL type database or something like Cassandra were often used in front of Mongo or Cassandra, and you can write to Hazelcast and read immediately back from Hazelcast in sub-millisecond times, and of course you can also then take all the data that's landing in Hazelcast and feed it into streaming logic and combine it with data coming in from Kafka, so that you can do these kind of real-time use cases in many different industries. So this kind of gives you an idea of what this data looks like in raw in Kafka, and I'm going to just jump back over and we will take a quick look at just one of those examples. So this is actually from the sample application code. And so you can see we're taking the trade in, and then we get the symbol, and we want to check whether or not this trade is considered a normal security type. So that's kind of a reference data. Give an example of how we're enriching the data that's arriving with other contextual data. And then we're able to do some grouping, and we're able to then do an aggregate. So each of those is going to be a stage, and will be able to then be parallelized and processed very efficiently. So you can see the code, it takes a little while to get used to the API, but once you do, it's very compact, and then of course incredibly performant. Most people, if you're familiar with Java util streams, as well as familiar with the Java 8 concepts and syntax, then it should be pretty easy for you to pick up this API. And then of course we also have SQL as another alternative. I am actually on the end of a 3-week business trip, by the way. So I spent a week in Turkey doing an engineering offsite, and then I've been in London and Sydney before here. So that's why I put all of the code into PowerPoint to make it easy to read, but also because nobody ever asked me to, well, why don't you edit that code and then make it do something different, which I'm a little too sleep deprived to be coding on the fly in front of a group, so that's my little way of preventing you guys from stumping me that way. But yeah, we'd encourage you guys to have a look and try this out. You can actually get these examples on our GitHub repo. There's a whole lot of different use cases, everything from like flight telemetry types of data to trading, or there's an example where we're looking at telecom data and trying to predict whether a customer is unhappy and likely to churn. We've got one where we're analyzing retail data and looking at propensity to buy. So all kinds of different interesting use cases. And then there's also simpler examples just of like how to read data from Kafka, how to write data out to different sources. And I also always want to give a plug for our excellent documentation as a great source of just examples, use cases, simple bits of code that you could then use. So Hazelcast doc is really a good place to go. Learn more about Hazelcast. We've got information on YouTube. We have a Twitch channel, which is going to get reinvigorated now that we have a new developer advocate who's just joined. Let's see what else. And then we have Hazelcast Cloud, so you can try this product out in the cloud as well. And there's free access for forever free for up to 200 megabytes of data, and that's going to go up, I think, to 1 gigabyte with our serverless launch. We'll be continuing to look to make it easier and easier for you to try it. You can install Hazelcast via like Maven and Gradle. You could install it by downloading it. You can install it using Docker from Docker Hub, or in Kubernetes. If you use Kubernetes, we have both a Helm chart and an operator. So there's a million different ways to install Hazelcast. There's also Brew. You could install Hazelcast and also install our management center and our command line that way. So however you want to try and install Hazelcast, we will make it easy for you to do and encourage you to try it. So I'm going to kind of pause there and see if there are any questions. Yes?
So when you mention about distributed, do you mean different geolocation? So let's say I write in the US East and then I write in US West. Isn't that bit latency a trade-off for the client?
Yeah, so when I say distributed, I mean, there's like, say, 3 nodes or 50 nodes in the cluster. The data will be split up into partitions. Those partitions will be spread out over the cluster so that each node has different data than another node. So if I were to go to our management center and if I were to look at the data that we have stored, the data is going to be distributed. There's entries on different nodes of the cluster, and if I add nodes, it will get spread out. The computations are also distributed across the cluster. What you're talking about with the geographic distribution, so we do have a replication cross cluster. So you can run clusters in different places, and then you can configure how data gets replicated between those, so that if I'm writing data here in Singapore and then somebody else is writing data in Sydney, they're going to retrieve the data locally, but we replicate it so that if someone tries to read the data here in Singapore that was written in Sydney, it will be available. There's always a latency there when you talk about starting to distribute things across geographies, because again, we have the speed of light. I don't know what the latency is between here and Sydney, but you could go and look up whatever the top telecom provider is between the two regions, and they'll give you you can literally look up. I've had customers who are like, oh, well, why can't you replicate any faster between here and these two cities? And I'm like, here, well, let me look up, in the US, I'll look up AT&T or Verizon, and I'll say, this is both the two of the top 4, network providers. That's the latency that they can offer you between these cities. So no matter how much money you have, unfortunately, Einstein comes into play, and but we also do have people running these clusters in not just in a highly available kind of DR type of configuration, but we also have people running clusters closer to where data is getting created for edge type processing. So for example, running inside of a petrochemical plant or inside of a warehouse where goods are being packed up and moved around, or run inside of a manufacturing facility or a medical facility. So those are all real world customers who are running Hazelcast in decentralized locations, and then they may replicate that data back to centralized clusters to kind of get a consolidated view of the data. And typically in that way, you don't do active-active, right? If you're doing that, it's more like, a one-way replication from the, kind of leaf nodes, if you will, to the central clusters that you have in that kind of edge architecture. We've even got a customer that runs us on a heavy truck, and they drive that truck out to a exploratory oil field, and it's analyzing, the data from the oil drilling equipment. And so there's like 60,000 events per second. Every single oil rig produces 60,000 events per second. So, but you don't want to take all 60,000 events and feed them back to the data center, because actually a lot of those events in the IoT world don't change, right? The RPMs of a pump or a motor, typically once they reach a certain operational speed, then it's steady, so, temperature readings, like once your engine gets warm in your car, the temperature tends to stay steady. And so like if I have a 200 hertz sensor giving me 200 events per second, telling me a temperature, but it's the same temperature for an hour, well, I can just aggregate it up and send like every 5 minutes back to the data center and say, yep, same temperature, hasn't changed. So why would I waste a lot of network bandwidth with sending the same data over? So that decentralized edge architecture, at the edge, you're processing everything and you're responding, and you can instantly respond and say, this oil rig, needs to be slowed down. And if it's not slowed down, it might fail, and that might cost $1 million. But, the central operational view is like, yes, all the oil rigs are looking good. They're all working properly. So that's a good question, and we do see more and more people looking at these kind of edge architectures and moving that data.
Just wondering if you could say a few words about the internals of, like, which language do you guys use? How big is the Hazelcast development team?
Yeah, so I mean, Hazelcast is written in Java, and the original APIs of everything were Java. We have data APIs that allow you to retrieve and write data in just about every language, and then we have SQL support that supports those languages. So now, if you combine SQL with every language, then you have that ability to work across languages. But under the covers, you're still talking to a jar file. Now we do have a native memory mode that's obviously not written in Java. It's moving that data. Some of it's in Java, but it's moving the data off heap into an optimized architecture where we handle all the garbage collection, and there's some native code there. As we start to introduce other optimized features like storage and things, we might occasionally write a little bit of optimized code. We can call other languages as well, so you could have a data pipeline, and then at a certain stage you decide, I want to take that data pipeline and call out to like a user-defined function, if you will, in whatever language. So you have customers doing this, calling out to C++ or C, a lot of Python being used, and then also just various kind of microservice or REST type APIs as well, gRPC, that kind of thing. So we can call out to other languages that way, and sometimes it's because we're calling ML, but in other cases it's just because there's existing code that's sort of works and nobody wants to rewrite it. They just want to call that code. And we run generally on Linux, but we occasionally have customers who will run us on other types of Unix flavors, including a couple of POCs that are underway right now, where we're running on ZOS, on the Unix system services in ZOS. So you could run us anywhere where there's a Java 8 or later SDK. Raspberry Pi, by the way, when you get into edge environments, ARM and Raspberry Pi or hardened ARM-based architectures are coming up, and we're starting to see people asking about ARM as well in the cloud. Intel's a big partner of ours, so we don't try to promote or push that kind of path, because we do see great performance with Intel technology, but we can run anywhere. In terms of the engineering team, I think almost half the company is engineers, or certainly if you include engineers and product managers, it's at least half the company. So most of the people are doing that stuff, and not an exec like me or a sales guy like Paul. We're kind of there's just enough of us to kind of get this software out to customers and keep them happy, and then of course we have a support org and all that, and consultants and things like that. But it's a very engineering oriented technology-oriented company, and it's also open core. So we have an enterprise product that offers things like automatic DR and other like zero downtime upgrades, rolling upgrades, and things like that. Advanced security and other features, but the core product anybody could try out is open source, and you know, we have actually a lot of companies using our open source today. I can never you know, from one day to the next, who you're allowed to talk about like changes so much that I try to avoid you know, naming names. But if I named our top 5 open source, you know, users, they would be companies that you would be like, oh yeah, wow, I've been using Hazelcast and I didn't even know. So, any other questions in the back?
Hi. When I create a pipeline, there are many stages, and probably one stage is super slow, and other stages are super fast. And in that case, we kind of want the engine to do some optimization in spreading out the jobs to different nodes.
Mm-hmm.
And is there a way that you could have a knowledge of if the stage will be fast or slow?
Yeah, so the question is, you know, when you've got all of these different distributed steps or stages of our pipeline, you know, how do you sort of tune when some things may be slower than others and optimize the overall end-to-end throughput? You know, the number one thing that we can do in that area is when we look at the jobs that are running, so the pipeline stages are visualized here. So each one of these little boxes is one of the stages of the pipeline, and you can see that at a certain point there's parallel pipelines where it goes in different paths. And so at each one of these stages, right now you could see what's going on with the whole end to end, but let's say you picked, you know, this step, you know, you could actually start to see processing time information for each step of the pipeline. And that information, all of this information that's being gathered in and the statistics are also available, you know, via, you know, JMX, and, you know, you can feed them into other things. Actually, we've got an example here. We're feeding the data into Grafana, but you could also be feeding that data into a tool that's also getting data from a profiler. So you could be combining your pipeline stage data information with maybe some profiling information, and that might help you to start to identify what's going on. The other thing that you can be doing is that you can be looking at where you have, you know, more computationally intensive or other types of bottlenecks, and starting to kind of, you know, analyze, you know, what could you do to maybe, you know, distribute that. And so one of the things that you could do is, for example, look at your data and see whether or not there is an ability to further partition. You know, so for example, I could get all the trades coming in from the Singapore exchange and all the trades from the Sydney exchange, and that might start to hit a bottleneck. But then what if I said, let me look at all the trades that are of a particular, you know, type of security or something like that. That could be another dimension of, you know, shrinking the amount of data down to allow you to parallelize it. But then you could look at other things, like, for example, is security, you know, in a particular industry? And maybe that's another way, if I started to get another dimension of the data, and then we could figure out some ways of taking that data and parallelizing the input to your pipeline. So there's techniques where you can say, this is a key that I want to use for you know, partitioning the pipeline, and therefore if I said, you know, all of the data from banks and all of the data from manufacturing and all of the data from hospitality and retail would be, processed different. So the industry, might be another way of processing it. But you could even go down to individual securities as your dimension for distributing and partitioning the data pipelines. So a lot of it is about thinking about the data and understanding what's the bottleneck. Is the bottleneck because I'm feeding it into a machine learning algorithm? What does that algorithm need? Or is the bottleneck just some really heavy aggregations that are happening? At the end of the day, like a lot of aggregation type computations are where you create a bottleneck. I'm trying to analyze and aggregate all of the information about a particular securities, and then I might want to eventually sum that up across a whole class of securities, or I want to look at, all of my customers, based on age. Well, as you start to go, I'd like to look at all my customers and all of the things that they're doing with data in real time, but I want to look at it for all customers from age, 15 to 50. Well, now you're adding more data in, and then, that's going to create more of a bottleneck with the data. And if you could break it down for different steps of your pipeline, then you could avoid that, and then you only want to do the final aggregation at the end, right? So you do a lot of parallel processing, and at the very end you want to say, and add that up for everybody within a certain range. And so there's tools in the product that allows you to do that kind of aggregation, and that's also a big area for us in terms of roadmap, is we want to provide more tools to help you to analyze and tune the product. I think over a longer term, we may eventually start to build some kind of automated query optimization or pipeline optimization algorithms into the product. But the key to doing that type of more automated analysis is that we need to kind of really have a lot of data from our customers on their use cases to be able to kind of figure out how to build those. And that's always the tricky part is, if you said, can you tell me exactly what you're doing with our technology? A lot of people are like, I don't really want to tell you every single thing that we're doing, or in some cases, I'm not even allowed to kind of get into a lot of detail. And so, that's always a challenge with, the automated types of optimization is you have to run them through a lot of workloads to try and make them intelligent enough. Otherwise, they could automatically make bad decisions. And so we don't want to necessarily do that. So that's why we kind of are favoring right now, giving you the tools to allow you to kind of do those optimizations, but also to help you find the bottlenecks. Because at the end of the day, the quicker you can find the bottlenecks, then the quicker you can optimize. I wanted to leave you back with the QR code in case, again, anybody would like to do the drawing. And because our marketing team will be disappointed if we don't make that available. The fewer people that do it, then the higher chances of somebody winning. But we would love to have you guys, enter the drawing, and in exchange, you will learn all about what's new in Hazelcast. All right. Well, thank you.
Just as a reminder, in case you have some question, Just I captured a little bit, so if some other questions are coming, this was, I think, correct about what you spoke about. You can correct me if I'm wrong.
Yeah, I mean, it all looks very good. Wow. The flag. You're, very talented.
Just listening. So, do you have, seeing this, do you have any other question that come to your mind? Graphic recording.
Graphic recording. Wow, impressive. It's fun. Kudos.
So, no other question?
Impressive.
I have actually one question. When you spoke about that, you create cluster with distributed and storage and compute. I'm real happy that you said that you can go to the speed of the light, because this is one of the things that nobody understands, especially in management. But when you come to this, when you have a complex companies, when you need to have a firewall, F5, and all this kind of shit that create latency inside the data center.
Yeah.
Is there some recommendation on how to install Hazelcast to avoid creating?
Well, if it's within a data center or within one cloud region, we have recommendations to do that. But just in general, I think you want a minimum amount of latency between the different nodes of the cluster. And then, I think we also do a lot of work to make sure that our, things like SSL support are, using the fastest possible libraries that can also take advantage of, hardware acceleration. And that's another thing when you talk about, security. Nowadays, more and more people are going to this zero trust model where even within a data center, they may want to have TLS communication, and so you definitely want to, be thinking about using the right high performance libraries and maybe good network cards and things like that. And then in the cloud region, it's just the same thing. You have to pick it, based on reading the specs. But we have, papers and recommendations on that. Other than that, I would say that, because we're not moving the data over the network, again, we do sort of minimize, the impact of those things.
Thank you. Any other question, or you want to have a normal life?
Maybe you covered it on this, but you were comparing your architecture versus the GFS architecture at some point. One of the slides.
It was a
Complex,
Spark,
complex,
but there was
smart,
also
right.
HDFS as a different dependency to Spark.
And one of the challenges that I faced in the past with this kind of architecture in multi-data center setup, split brain management.
Yes.
So is that the problem that Hazelcast addresses, or the management nodes still have the same selection process?
Yeah, so Hazelcast, each cluster, is, replicating and communicating, and so if there's a network partition between the nodes, we have to deal with that, and we have two different algorithms that we use. One of them for better performance and availability is based on the Praxis algorithm, and so it's an AP-based behavior. And then we also have a CP-based option, so that if you really care about, if I write to the data and I can't make a backup copy, and I can't ensure that everything that write is 100%, that there can't be any data loss or any dirty reads, then you can have a CP option. So we have what we call our CP subsystem, which is based on the RAF algorithm. So we kind of allow you to kind of make trade-offs there. The other thing that we do offer, even with the AP system, is there's a way that we can have some of the logic executed using something called an entry processor, which is basically ensures that each partition, the data writing to that partition, will be queued up so that you know, if you're having a bunch of writes that they all end up having to go into a partition thread, and since it's all working with one thread, then you know it can't possibly execute ahead of other instructions. And so that entry processor can offer very high level of consistency, but what you have to then do is tune how many partitions you have based on your compute patterns and your data. So that does require some tuning there, but that's another technique. Do that, you know, ensure that kind of consistency. And then we're constantly looking at, you know, different use cases from customers in this area, and trying to figure out how to make that easier. So in the future, it's going to be probably much more, you know, a tunable thing where each, you know, object or data type that you create you'll be able to say, do you want this to be CP or AP? And you know, there's another interesting theorem called PACE-LC, which talks about not only the trade-off of availability and consistency, but also latency, how those choices impact latency. Because sometimes people think that you know, it's just a choice between consistency versus availability, but actually, when you care about latency, then you know you have to kind of have a more nuanced view of those things.
Thank you. So, yeah, thanks everyone for coming.
Thanks, John.
Okay. Thank you for hosting, and
Thanks.
thank you for hosting.
Thank you for hosting.
I'm very excited to actually be doing these face-to-face again.
So we officially close for internet, but you can still stay at least a little bit, I think, if you want to discuss. So thank you, John. Thank you for